Hello guys, welcome to our webinar dedicated to a new update of Visual NAND Reconstructor software 8.2. And today I will show you new features, new things which we implemented in this update. Firstly, let me begin from new resources. As usually, we have added new resources to the software, such as XOR keys, code words, new NAND chips. In order to be able to get access to those resources, to use those resources, you need to download from your client portal a new version of a database file and unpack it in a folder with Visual NAND Reconstructor. Then these resources will be available in the software. Also, there are new pinouts in this version. Some of them we got from our valuable clients, thanks to them. It's a flash matrix company and bought data recovery. So thank you guys for this contribution. You made life of our users better with this pinouts. I hope so. Also, recently we got one chip, which is very rare. It looks like it's very rare because it's the first time we got such a chip in our whole history. It's a Micron chip 2C, 84, 48, and so on. And for that chip, it was necessary to develop new protocol. So new protocols were developed. And from now on, if you'll get chips with such protocols, you will be able to read them. But the main feature of this update, it's a breakthrough in our AI XOR generating tools. Firstly, let me tell you several words about the tool itself. As you remember, as you know, controllers use scrambling for when they write data into NAND memories, right? And basically, there are two approaches how you can descramble data. The old one, classic one, let's say, this approach implements creating in advance some binary XOR key, and later you can use this XOR key in order to descramble the data, raw data which you get from NAND memory. So basically, it's necessary to have a database of XOR keys. It's necessary to have to analyze devices and create using those devices binary XOR keys. And later, if you will get a similar device, those keys could be used and you can XOR the data. The new approach, which we use here in VNR, AI XOR generating, does not require any binaries or donors for XOR key creation. XOR key could be created right on your patient device, specifically for your patient device. And of course, it's much better because you don't need any donor drive, right? You do not depend on existence of XOR key in database in your tool. So even if the device is not supported, you can run this XOR key generating, and it will be done. It will be done for you. But the problem was that it's quite time-consuming and resources-consuming process. So it took some time, let's say, for generating. But with this update, the new version does it much more faster. For some cases, it's like 1,000 times faster. So the algorithm is better, hugely better, let me say like this. And so basically for some controllers such as, I don't know, Silicon Motion, AU, you can basically try to use XOR key generating all the time. You can try to avoid using database, but still for like some time before, you still had two options. You could use either generating of XOR keys or using it from database. And the thing is that for new devices, for newer devices, the old approach may not work at all, because each specific device may use unique key, a unique XOR key which was created by controller specifically for that device. And even if database, if you will get some donor device and you will take the key, you will create the key using the donor device, later it will not be possible to use it with your patient drive, because both of these devices may have unique keys, and your donor key will not be compatible to your patient drive. And why does it happen? In case of Silicon Motion controllers, for example, quite popular one, SM3281L, it happens because in case if it has bad columns, XOR key is created for bad columns too. It looks like this. So the standard, it looks like this. And firstly, let me explain, in order to understand the difference of the key for this controller, firstly, let me tell you several words about the standard key. Standard Silicon Motion key or any other key which we could see before. So in a standard case, if one data area, let's say, has 1024 bytes, size is 1024 bytes, and it has some number of bad columns, the key still generated for 1024 bytes only. So the key is not generated for the bad columns. The XOR key size is 1024. So that is why you can use basically, the key could be standard, and it does not depend on number of bad columns. It doesn't matter if you have 5, 10 bad columns. It doesn't matter how those bad columns are distributed. You can just use the standard key. I mean, firstly, you need to remove bad columns, and later you can use a standard key from database without any problems. Everything works just fine. But when it comes to SM3281L controller, it works differently, because that controller, if there are bad columns, generates XOR key on bad columns too. So in case if data area is 1024 as usually, and it has like 1, 2, 3, 4 bad columns, then XOR key will be generated for 1028 bytes. And of course, if your donor drive has some bad columns and your patient drive doesn't have it, then the XOR keys will not be compatible, and vice versa. Also, the XOR key is generated differently for different planes. Different planes have different XOR keys. So different devices, different planes, different number of bad columns, all this leads us to the situation when you just cannot use normally XOR key from a database, and you need to generate it each and every time. And it was possible with even older version of VNR, but it required quite a lot of preparations and transformations. Firstly, it was necessary to create key, then specify where are bad columns, and it was quite a hard procedure. Now, with new version, you can do it just straightforward. Firstly, you need to remove bad columns, as usual, like you did in a standard way, and then just generate XOR key pretending that there are no any bad columns at all. VNR will take into account those bad columns, but for you, everything will be just standard. So with a new version of VNR, you can use it easily and fastly and without any problems, I hope. And yeah, that's the only actually way to solve cases with this controller. If you try to use XOR key from database, if you try to use the old approach, it will just not work. You need to have a VNR with a new version, and only then you can recover such cases at this moment. Another implementation, another improvement that we got with a new version is made for AU controllers. These ones may use XOR keys created not, let's say, sequentially. So here, again, firstly, let me show you the normal AU XOR key, which looks like this. That's the bitmap of, let's say, normal AU XOR key, where all the pages are generated, are written, let's say, sequentially in a normal order. So I tried to show it with this diagram that pages are generated sequentially. Everything is written here sequentially. But some AU controllers may create specific XOR keys where let's say key is the same, but it's divided by groups of pages, and those groups are mixed. It works a little bit in a little bit more complex way. I mean, the explanation is simplified, but it's just easier to understand it if I say that controller divides XOR key by groups of pages and then mix it and then apply to the data. And it looks like this. So controller, the key was divided by groups, and then those groups were mixed. And this division and size of groups and the distribution of those groups of pages is individual for different devices. So again, you cannot use here standard key from database. Again, for each and every device, key should be generated specifically. And only VNR can do this. Some time ago, it was not possible to fix such cases. Now you can do this easily. So that's the new improvements of VNR in this update. Firstly, it can generate XOR keys much more faster than previous version. Also, it can generate XOR keys for Silicon Motion controllers where there are bad columns, and XOR key was created for those bad columns too. So for those cases, this procedure must be used because without it, it's just not possible to solve cases. And also you can solve now AU controllers where XOR key is mixed. And yeah, of course, the last thing, it's improvements in the interface of block manager, long-awaited possibility to check these checkboxes straight in here, let's say, right, by just normal clicking in these checkboxes. A lot of users wrote us that they waiting for this improvement, for this update of the interface, and finally it's done. Now, if you need to apply inversion or little endian format or mask, you can just make one left click in the checkbox and it will be done. So block manager is improved too. That's the description of new features, new things that we added. And now let me demonstrated. So firstly, I will show you the Silicon Motion case with bad columns, where you need to firstly remove bad columns and then generate the key. And this is the case where a key is generated for bad columns too. So if we open the dump and scroll it a little, we can see some blocks with data, some blocks with empty blocks with some garbage pattern. And then we can see a lot of those bad columns. And XOR key is generated for those bad columns too. And in order to fix this case, firstly, I need to remove bad columns. But for these specific cases, I will create transformation chains in the solution here on workspace for each plane individually, because due to that bad columns and XOR key generated for bad columns, the structure of data area, ECC area, and so on will be different from plane to plane, because one plane will have one set of bad columns, other plane will have other set of bad columns. And the structure is used for XOR key generating and things like this. And one chain may have just one structure. So firstly, you need to split this physical image by planes, and then perform all the transformations for each plane individually, and then you unite planes back and proceed with block management step. So in our case, we can see that the device has two planes. We can see that because by bad columns distribution, we can see that one plane has bad column, then this one is empty. Oh, let me find some other place. Yes. So here we have the data, bad columns, then empty plane, and then we have continuation of the previously seen bad columns like this. So we can see that there are just, let's say, two patterns of bad columns. One and second, where we don't have bad columns at all. In case if we would have like one bad column here, then something is here, then something else is here, then something else again, and only after three different bad column distribution, after three different planes, we again see the first bad column, which we could see initially here. So it would suggest us that the case has four bad columns. In our case, we can see just two patterns of bad columns distribution, like this one, and nothing. Well, actually, in this case, we can see that second plane is just empty, most probably. Data is not written here. And yeah, so I guess that we will do nothing for second plane, and all the data will be taken from the first plane. Anyways, we can see that there are two planes, and in order to divide this dump by two planes, we need to use this element. So I select a physical image, divide, and the default options here set up for dividing by planes. So in the parameters, we can set the size by which the dump will be divided, and the number of parts on which it will be divided. So it will be divided on two parts, and the division will be done by approximately 4 megabytes, so by block size. So it means that 4 megabytes from one plane will go to the first result. Next 4 megabytes will be go into the second dump, then next 4 megabytes in the first, next 4 megabytes in the second, and so on. So it will just distribute like this whole dump by 4 megabytes into two results. And as you understand, I hope you understand this, that the dump consists of two planes, and it has one block from one plane. We could see it here basically. So one block from one plane, second block from the second plane. This block has size of 4 megabytes, approximately 4 or 5, approximately 5 actually. And then next 5 megabytes. So it will just split this dump on two parts and by 5 megabytes. 5 megabytes go to the first part, next 5 megabytes go to the second dump. Then next one go back to the first dump, first result dump, and next 5 megabytes will go to the second dump. And as a result, we're gonna see two dumps. One will have data and one will be just empty. So this is the second plane. And as you can see now, it will be just nothing here. So yes, it's totally empty. And all the data now is located in this dump, because this one has data from one plane. And now the bed columns go sequentially without any interruptions. So now I can just connect bed byte column remover and remove bed columns standard way like we do usually. Just one thing, I need to set here in parameters number of planes. As you understand, I need to set it 1 to 1, because there is data from one plane only here. Then I click on edit, scroll to some place with data, and as usually I can select bed columns manually, or I can use automatic search. Automatic search using these presets. So silicon motion, preset, run auto detection, and some bytes were detected as bed columns, so these ones, and some bytes probably bed columns. So in our case, it's not actually bed columns, but it's this is ending of ECC. ECC has several one empty byte, actually FF byte, and one byte with one FF bit, actually 0 bit, sorry, 1 bit. And I need to remove these false positive bytes, so because they do not belong to bed columns. And to do this, I can do right click and uncheck all of this type. And now all these bytes were unchecked. For the FF, I will do the same. And there is an interesting thing here that there are two bytes which look totally like bed columns, and those bytes are located in the service area. And the thing is that it's not actually bed columns, but it's a part of service area. So they should be unchecked too, because if you will remove it, the service area will be changed or corrupted, and the ECC, which is here, will not work for the service area, for this part. So these bytes should not be unchecked. And basically that's it. That's all I need to do with bed columns. Now I click on add all bed columns, and all the bed columns now checked. So everything is fine. And the next step would be, after the VCR, would be ECC search, right? So I will click to find ECC, select Silicon Motion, and click on Find. Okay, two code words were found. One is for 128 bytes, one is for 959 bits. It's approximately 119 bytes and 8 bits. In our case, I checked before, we have 121 bytes for ECC, so I need to select this one. ECC is selected. I can check now ECC map, and I can see it's done already, and ECC works just fine. So all bit columns are removed, and everything is good to proceed. The next step would be the XOR creation. But firstly, I need to set up structure of this case. The structure was not created automatically because the code word, the ECC has code word for the service area also, yes, here. And then and the structure actually here is quite a little bit exotical, let's say. So it was not detected automatically. We need to do this manually. But it's actually quite easy. The page begins from data area is usually, and the data area has size 1024 bytes. The next structure would be ECC. It's 128 bytes, 121. Why do I keep saying 128? Okay. And the strange thing here is that after some experiments, we found that after the ECC, there is one empty byte, which should be just skipped. So you shouldn't add the next data area right after ECC, but we can add one empty byte with the size 1, like this. And after this step, we can just copy these 3 structures and paste till the end. You can see that this all the colors now on right places. I mean, the ECC ends where it should be ending, and everything is there good. The size of service area here is 10 bytes. So 10 bytes. Let me check it. Check. Yes, the service area has 10 bytes, and then there are 21 bytes for the ECC of service area. So let me set SA 10, and then SA ECC 21. And that's the full structure for this case. The last thing I need to set is the header. It's located on the standard position here, the first byte of service area. And then there are 2 bytes for the LBN. So typical Silicon Motion structure, typical Silicon Motion location of header and LBN. And that's it. So the structure is defined. Now I can connect SM XOR and run XOR key generating. It will take some time, approximately 3 minutes. Without bad columns, it would be faster, but when there are bad columns, it's necessary to take them into account. So it's a little bit slower. But still, for 3 minutes, you will get all full XOR applied to this specific case for bad columns. So it's actually a very good result, because before it might took quite a long time for creating such a key for this specific case. So let me run it and see then with what we will get. When the key will be created, I guess I will not be able to say anything, because this generating takes a lot of resources from computer, so sound may be not good. But actually there is nothing to say here, so let me just run the key generating and wait for the result. Okay, so the key was synthesized, and it took approximately 5 minutes. On a more powerful computer, of course, it will be faster. This one for demonstrations is not actually best for the data recovery cases for XOR key creating. But still, it was done for quite a short time. So now I need to apply it, and the key is applied. So now basically, if we open it, we will see some patterns of data. However, this case has mostly pictures, and pattern of pictures actually look like quite noisy, because it's compressed pictures and JPEG pictures. Okay, after the XOR, after the unxoring, we can proceed with block management actually. But firstly, let me connect this data to. I guess I will bring here empty bed column element just to make it look same, and then copy paste these two. After that, I will unite it, and actually I can unite it by DOM. So this element firstly will have a whole plane from this chain and this empty plane. The unite size should be set to the DOM size. Yes, now we can have data from the first plane only, and the second plane looks like it has data, but in fact it's not data, it's those empty areas which are filled by this kind of garbage pattern. Okay, so the key is created, both chains are united, and the last step would be the block manager. So I need to bring it here, open. It has some changes in interface. So now you can see that this the first button you need to press is highlighted. So let me create a table. After table creating, it offers me to determine types of blocks. Let me do this. So it will detect if blocks have, if some specific block has data, or if it's empty block, garbage block, and so on. This information might be useful when you perform filtering. If, for example, headers or LBN range doesn't help you to uncheck unnecessary blocks, block types might be useful. So you can set, for example, to use only blocks with data, and all other blocks will be unchecked. All right, so that's the table. And here we have all the information about each block. So this column, use column, stands for either we use the block in logical image or not. If each line here represents one block, and if it's checked, then this block will be placed into final logical image. If it's unchecked, it will be skipped. Initially, all the blocks are checked, and our goal here, our task, to uncheck all blocks which we don't want to move into logical image. It's the first thing, and second thing, we need to arrange all these blocks, all these lines in ascending order by LBN. So the first block will have file system, the next block will have continuation of file system, and so on. So the second column stands for banks. Sometimes there are several banks of blocks in one device. In our case, I guess it will be just one bank, so bank 0. Here we have logical block numbers, headers, the new feature of block manager, file system signature. So actually here VNR reads from position 510, 511 values from positions 510, 511, and if the values will be 55 AA, that block will be highlighted. So it may help you to, when you will search for blocks for the block number 0 with blocks with file system. Before we did it manually each time, then we decided why don't we just set it automatically? So yes, now it's predefined here. Then we have a physical address, physical block number, and the type of block. And firstly, if I scroll the list of blocks, I can see that values of LBNs are quite large. I don't see most of them like F something. And it means that LBNs are inverted. Most probably they are inverted. And inverted back. As I told you, now we can just make one click here on the inversion operation, and the same we should do for the header. So now it's all was inverted, and now it looks better. And basically now we can start the filtering process. Firstly, we can filter it by the headers, and this controller has headers. We can see 40 here, 60. It's a little bit different from that old Silicon Motions where we have a range of values. In this case, we have mostly 40 and 60, but also 41 and 61 are possible. So we'll set 40, 41, 60, 61. And with this setting, only these blocks will be checked and any other will be unchecked. Like this one, for example, and all these ones. Now let me arrange it by blocks and check the range of LBNs. Oh, I see this block has signature 55AA, number 0, so yeah, it has the FAT tables file system structure. Now I want to check the range of LBNs, and we can see that the largest number here it's 0771. So it looks like that the LBN range would be from 0 to 07 FF. But actually, you see all these blocks were unchecked on previous steps, so LBN filtering is not very important here, but still, let's do this just in case, just to make it right. And yes, filtering is done now. Let's sort the blocks. Sort blocks. And now all the blocks go sequentially. We have some pattern written here in this area, and then some data. Now let's check the chain. So to do this, I will select the first block, then click on check block chain. And we can see that there is a gap between these two blocks, quite a big one. Yes. So for now, let's just remember that there is a gap here. Keep checking. Yeah, and we can see that probably this block is the last one and this one is just empty. So I can unselect it and click on insert missing blocks to fulfill that gap. And now it should be fine. If I check blockchain, I will see this message. So the last step would be to build logical image. Logical image is done. Let's go to file system viewer. And we can see that pattern, which we could see in bitmap 77, and some data, some pictures. So you could see, guys, that the XOR key synthesis with bad columns works. We can recover data efficiently and quickly. And Block Manager now has these new improvements. That's the thing which we created for you. Also, to demonstrate the speed of new XOR key generating, I can just show you in one ready case how much faster it can work sometimes for some cases. Depends on case, depends on quality of dump and number of blocks for verification. So sometimes it could be even like this. Silicon Motion, sorry, yeah, it's all correct. Now let me check. Oh, sorry. See how strong habits might be. Silicon Motion XOR, run. And it's done. So just several seconds, XOR key is synthesized. I can apply it. And now if we will compare results from the key which was just generated and the key on this element which was taken from database, we can see that the results are quite same. So it works. In short, we can say that it works quickly and correctly. That was the story about Visual NAND Reconstructor 8.2. If you still have not updated it, please do. Try to use it. Send us your feedbacks, positive, negative, any. I guess any feedback will improve the VNR. And what? Stay in touch. See you on the next webinar. And good luck. Bye.